This video will cover several foundational concepts for post-tonal music theory: octave equivalence, pitch class, integer notation, enharmonic equivalence, and mod 12. In all music, we have a concept called octave equivalence. This means that all pitches separated by an octave are considered functionally equivalent. Hence, they have the same name. For example, all these pitches are called C. On that note, such a group of pitches is called a pitch class. This is different from pitch, which is register specific. This concept of pitch class is used in a different way for post-tonal music. Instead of letter names for notes, we use a system called integer notation. In this system, letter names are replaced by numbers or integers. In the chromatic scale, we can see all possible pitches within an octave. Instead of C, C sharp, D, D sharp, we would call these notes 0, 1, 2, 3, up to 11. These integers represent a sort of fixed dose system, in which C is always 0, B natural is always 11, and so on. Sometimes 10 and 11 are written as T and E to make listing pitch classes more clear. This system is useful in this new context because interval quality is no longer a focus of analysis. Instead, we're more concerned with the exact number of half steps. Comparing the ascending and descending chromatic scales illustrates another foundational concept of post-tonal theory: enharmonic equivalence. In tonal music, F sharp and G flat are different pitches because they either belong to or suggest different keys. As you can see, with pitch class integers, F sharp and G flat are both 6, and the same is true for all enharmonic pairs. The lack of functional harmony in post-tonal music eliminates the need for this distinction, so all enharmonic pairs are considered functionally equivalent as well. Looking at the pitch classes of a chromatic scale spanning multiple octaves, every 12 notes, the cycle of integers 0 to 11 repeats. When dealing with pitch space rather than pitch class space, we sometimes come across notes labeled with integers less than 0 or greater than 11. Converting these pitch integers to pitch class integers requires the arithmetic function we call mod 12. To use mod 12, whenever you encounter a pitch integer less than 0 or greater than 11, add or subtract 12 as many times as needed until the integer is within the 0 to 11 range. Here it is in action. For this example, we'll call middle C 0, then use both negative and positive integers to show the pitch relationships around it. Now we'll use mod 12 to convert these 3 pitch integers to pitch class integers. 14 mod 12 equals 14 minus 12, which equals 2. Negative 3 mod 12 equals negative 3 plus 12, which equals 9. Negative 28 mod 12 equals negative 28 plus 12 plus 12 plus 12, and we get 8. An everyday clock face uses the same kind of mod 12 system, and as such, it provides a valuable tool for visualizing pitch class space and relationships between pitch classes. Instead of 12, start with 0 and put all the integers around the face like hours. Now take a fully diminished 7th chord beginning on C, for example. By circling the pitch classes, we can see the relative size of the intervals present, any potential symmetry, like this perfectly symmetrical chord, and other patterns. Thanks for watching!